Okay, so here we have nanomaterials, and here some characteristics are written or why nanomaterials are important. So surface to volume ratio you have studied, right?
Yes,
So
sir.
here you see three cubes are there. The largest one is of 3 centimeter, each side is 3 centimeter, the middle one each side is 2 centimeter, and the smallest one each side is 1 centimeter, right? Now if you calculate surface to volume ratio for individual cube, then you will find that the smallest one has largest surface to volume ratio, which is 6. Okay, let me make it full screen. So you see now the smallest cube has largest surface to volume ratio, 6:1. The middle one is having a surface to volume ratio of 3:1, and the largest one is having a surface to volume ratio of 2:1. Okay, so you can see with decrease in size, okay, the size is decreasing and surface to volume ratio is increasing. Okay,
Yes, sir.
so this is one of the characteristics. Okay, so these are the main points why nanomaterials are important, or characteristics of nanomaterials. So I think recently I posted one video in my YouTube channel. I think also
Yes, sir.
given to
I
you.
saw, sir.
Yeah, so there also you will get these things. Okay.
Yes, in your channel you are posting.
Yeah, exactly. And also this density of states. Okay, and we have also discussed this. So I think density of states. Have you learned this concept in solid state physics?
Density of states.
The states, yeah.
We haven't learned, I think, sir.
Okay, then anyway, it will be useful for MSc students, or you can talk about like few lines. Okay, I think it's also discussed there in that video, no, in my YouTube video. So on details, you can check that. Then okay, band gap. So the left one is for semiconductor, no, bulk material. Bulk material has band structure like this, but when we have a nanoscale semiconductor, the band gap is increasing, right? So I think this is also discussed in my video, in my earlier video, which is posted in YouTube channel. Okay, and these are the like no very these are the energy band structure of metals. No, bulk metal, valence and conduction band are overlapping here. When you have large metal cluster, so large metal cluster means there will be around 100 atoms. And for large metal clusters, the energy bands get to become discrete. Okay, they become quite discrete. And for small metal clusters means they have about 3 atoms and so on. Only 3 atoms, and they have very discrete electronic structures. Okay, so why they get discrete electronic structure? That is also given in my video, no, YouTube video. Maybe you can watch that later. Or anyway,
Okay, sir.
before your presentation, we'll discuss these things in details, okay? But it is also already there in the PowerPoint or in my previous videos, okay? So here you see this figure is for gold nanoparticles of different sizes, no? 20 to 80 nanometers, and they are changing colors. You see, the color is
Yes.
changing from orange to red, and then some violet, some not violet, some reddish orange type of color. I don't even know what color this is called exactly, but reddish type, reddish or reddish violet, not reddish orange.
Is it purple, sir?
Reddish violet type, yeah, something like that. So this change in color, if somebody asks you why is there a change in color, change in color is because of change in particle size, nanoparticle size, and when you are changing the gold nanoparticle size, in that case, that particular okay, I will come back to, because to understand this, we have to know a topic called surface plasmon resonance. Okay, so this is because of surface plasmon resonance. So what happens in surface plasmon resonance? So surface plasmon resonance is observed in very small metal nanoparticles, or simply metal nanoparticles. Of course, nanoparticles are small. Now, when the size of nanoparticle, metal nanoparticle is smaller than wavelength of radiation, okay? Because you see, in order to observe these colors, you have to do UV visible absorption spectroscopy measurements, right? UV visible means you will illuminate your, you will apply ultraviolet and visible light to your sample. Okay, we have this instrument actually in our laboratory, but
Yes,
this
sir.
time we could not use because of this lockdown. No?
Yes, sir.
So anyway, so we can do UV visible absorption spectroscopy measurements of these gold nanoparticles, and this from UV visible absorption spectroscopy measurements, we can calculate the absorption wavelength, absorption wavelength of the nanoparticles. And this absorption wavelength
Yes,
is
sir.
dependent on particle size. Okay. And that thing we will discuss after a while, which is called surface plasmon resonance. What is surface plasmon resonance, etc. So gold nanoparticles of different colors. So why different colors? Okay, I will discuss it during surface plasmon resonance. Okay. So this first figure is for metal nanoparticles. The second figure is for semiconductor nanoparticles. Not of your interest because you are working with gold nanoparticles.
Yes.
And for semiconductor nanoparticles, what happens? You see difference in color. Difference in color means
Mm.
they are of different sizes. So you see blue color and you
Yes.
see red color. Okay. So this blue color means nanoparticles are the smallest, and red color here in right, extreme right, red color means nanoparticles are largest. Okay.
Yes,
And
sir.
depending on size they exhibit different colors, and this and they show such colors if you take this nanoparticle samples to a dark room, no, and you illuminate them with UV lamp. Okay.
Yes, sir.
So actually I also wanted to do this experiment this time because we have both dark room and UV lamp with us in our laboratory, but we could not do it.
Yes, sir.
Okay, so why you choose gold nanoparticles? So that can be given a title of motivation.
Mhm.
So gold is a chemically versatile material.
Yes.
It has excellent electrical properties. Then it can be coupled with a variety of chemicals. Okay, so these are some of the advantages of using gold. No,
Mm.
because the external might ask you, why do you use gold nanoparticles? Why not silver, or why not, let's say, copper, like that? Okay, so then you have to say these points. Then another gold nanoparticles exhibit surface plasmon resonance, which offer applications in various fields like biological field, medical field, and material science related fields. Okay,
Yes, sir.
so these are some of the reasons, and also some applications of gold nanoparticles here. So gold nanoparticles find application in something called photothermal therapy. Then, so these things are discussed in your, I think, in your thesis, no, introduction. What
Yes,
is
sir.
photothermal therapy, drug delivery, then
Yes.
electron microscope, cancer imaging, then protein detection, pollutant material detection, also used in photocatalysis. So these are the various fields in which gold nanoparticles find application. Okay.
Yes, sir.
So that's motivation. Motivation means why you want to work with gold nanoparticles. Okay.
Mm.
Then
Yes.
another slide you can see. This is also coming under the motivation part. So you see these are the gold nanoparticles of various shapes. No? These are like cubes. These are like hexagons. These are like I don't know, called pentagons, or Then these are triangular. Then these are no called something like dog bones. No, these are like dumbbells, and these are called bipyramids or something. So given in the uh, caption here. So that means gold nanoparticles of various shapes can be formed, which is an advantage, no, depending on what application, why you need it, for what application, etc. Okay, so
Yes.
this way you have to show motivation also, like why you have decided to work on gold nanoparticles. Okay, then experiment after introduction. So with here you have finished introduction part. Okay,
Yes.
then after introduction you have experiment. So okay, let me make this bigger.
Mm.
So actually, MSc students did this synthesis in laboratory, and this is the synthesis method. I think it will be given in your thesis also. So okay, the chemical reaction. Okay,
Yes, sir.
so now I will show you this video. Let me see if it runs or not. Yeah, you see this video.
Uh,
Okay, so this is the Turkevich method. Okay, so whatever we have written here already, we employed modified Turkevich method to synthesize gold nanoparticles. So this is the Turkevich method, and this is the experiment that we performed. Okay,
Yes, sir.
so yeah, so this will be there in your presentation. The method, the video you may present or you may not, but it's good for MSc students. They can show that we have actually done this experiment.
Yeah.
So this is gold nanoparticle formation mechanism if you have done the experiment. So this will also be included in your thesis, experiments part.
Yes, sir.
Not experiment, sorry. This will come under result and discussion part. So in result and discussion part, what is how these gold nanoparticles are formed. Okay. Now
Mm.
optical properties, this is very important to understand. Okay. So let me explain this to you quickly today. Okay.
Okay, sir.
Okay. So you know about band gap, or sorry, about band structure of materials like metals, semiconductors, or dielectrics or insulators. So here you have seen dielectrics. The dielectrics means also insulators. Okay.
Yes, sir.
So in metals there is no energy band gap. Why? Because the valence band and conduction band overlap. You see, no?
Yes, sir.
The red one is valence band, the blue one is conduction band, and in between there is an overlap of bands. Okay.
Yes, sir.
In semiconductors, this is the valence band, the red one, the blue one is the conduction band, and in semiconductors there is a gap, right? Some small gap, and along this gap, what happens? A charge carrier like an electron can be excited from this valence band to the conduction band. Okay, depending upon how much energy you supply. Okay, so this is called band gap. This gap, no? And band gap of most of the semiconductors are from 1 to 3 electron volt. Of course, there are some semiconductors that have higher band gap, like zinc oxide, which is a band gap of 3.3 electron volt. So generally within 3.5 electron volt, this region is okay.
Mm.
But now insulators or dielectrics, this gap is quite huge, quite large. Large means here we have to talk in terms of energy. Okay,
Mm.
energy means suppose if say in semiconductors it is like up to 3.5 electron volt, but in case of dielectrics or insulators, this gap or forbidden gap may be about 7 to 9 electron volts, which is quite huge. Okay, and since 7 to 9 electron volt means you have to you have to apply a very huge amount of energy for an electron to be excited from valence band to the conduction band. Okay, you need a very huge amount of energy, and that is why dielectrics or insulators, they do not conduct electricity, right? We know why metals conduct electricity. Conductors are metals because now there are a lot of electrons for a lot of conduction electrons for electrical conduction. Now, conduction electrons means they can move around through the metal crystal and they can contribute to electrical conductivity. So semiconductors become conducting if you supply some heat or energy, so that valence electrons can move from valence band to the conduction band. This conduction band electrons can take part in electrical conduction. But in insulators, this gap is so huge that it is very difficult to excite electrons from this valence band to the conduction band. Okay. So now you understand more or less why this the difference between this conductor, semiconductor, and insulator band structures. Okay, for you, for your and other those MSc students, so this thing is important. Understanding the band structure of conductors or metals is important. Why? Because we are working with gold nanoparticles, and gold is a metal, okay, or it's a good conductor. So this is important for you and for other groups like this. Now, Rakib and in the for them this is important. Okay, so for us, for you, this is important. Conductors. Okay. Anyway, this one. Okay. So now what happens? There is this phenomenon called surface plasmon resonance. Okay. So what is surface plasmon resonance? So you see here this golden color. This is the gold nanoparticle. Okay. So what is going on here? So when do you observe surface plasmon resonance? When we do UV visible absorption spectroscopy measurements. Okay. So what we do in UV visible absorption spectroscopy measurements, if I tell you quickly, we take gold nanoparticle sample in a cuvette. Okay, cuvette is a small vessel made of quartz generally. So we take that sample in quartz vessel or cuvette, it is called, and then we put it in the instrument at a particular place, and then we start the instrument, and the a wavelength scan is done. Wavelength scan is from like UV visible, no, from ultraviolet range to visible range of electromagnetic spectrum, from 200 nanometers to generally 800 nanometers. Okay, in between we do a wavelength scan, and what happens if we do wavelength scan at a particular wavelength of particular wavelength? What happens? Particular wavelength means resonant wavelength, or this resonance. What is the resonance means? When the particular wavelength of electromagnetic radiation becomes equal to or matches the electron oscillations. Okay. So what is resonant? That is what I am trying to explain you. So electrons, we know now, we have just learned about the band structure of metals.
Yes, sir.
So metals have a lot of electrons, right? A lot of electrons, a huge concentration of electrons. So, and this, what you can do, you can make this electron cloud or electrons to oscillate about their mean position. How you can do that? If the frequency of the electromagnetic radiation matches the frequency of oscillation of the electrons.
Yes, sir.
Okay, Oscillate means they will, perpendicular oscillation, this oscillation. Like in simple harmonic motion, you have learned about oscillations. So they will oscillate about their mean position. So what will happen at a particular wavelength, suppose at 530 nanometers, no? That is the generally that is the wavelength of oscillation for gold nanoparticles between 30 to 40 nanometers. Okay. So what happens during such oscillations? So because this is a gold nanoparticles, and here we have the nucleus and we have the electrons. Okay, so the electrons displace about their mean position. You see the electron cloud e minus, no, e minus, e minus, e minus, this blue region here. So because of this resonant frequency or wavelength, whatever you call, no, so frequency and wavelength are depend, we can interchange these two terms, frequency or wavelength. Because of this resonant wavelength or frequency, the electrons are displaced from the positive charges of the atoms. So GNP means gold nanoparticle, no? Gold nanoparticles, there are atoms, and electrons get displaced. Okay, so electron cloud you can see here, and the positive ions are here. And electrons, so it is a kind of polarization. So polarization, separation of charges,
Yes,
separation of electric charges. Maybe you have studied in your solid state physics in last
yes.
semester. So
We
that is yeah. So a type of polarization happens, and this polarization results in separation of this electron and positive electrons, which are negatively charged, and the positively charged nucleus or the cationic lattice of gold nanoparticles. Okay, or ionic, sorry, ions of positively charged ions of the gold nanoparticles. Okay, so they are separated, right? And these electrons are negatively charged, and these are positively charged. Okay, the
positive ions.
positive, yeah, the ions. The
Yes, sir.
ions in the metal are positively charged, but electrons are negatively charged.
Yes,
And
sir.
therefore, because of this, opposite polarity of charge, what is there? There is a Coulombic force of attraction. Okay. So no, between charges, either they are same nature. Same nature means positive or negative, or they are of different nature, like positive and negative charge. Okay, so there
Yeah.
is always Coulombic interaction, and in this case there will be a Coulombic force, no, of attraction. So a kind of restoring force. Restore means it wishes to bring the charges back to their original positions. Okay, so there is a Coulombic attraction between the positive and negative charges. Okay, and because of this, a restoring force or a force is there which tends to bring back the charges to their original position. Okay,
Yes.
and this results in oscillation of the electron clouds with respect to the positively charged ions. Okay, so you understand this? So this can happen only at a resonant frequency. First, resonant means the frequency of electromagnetic radiation has to be equal to the frequency of oscillation of the electrons. Okay, and when this happens, so these charges get separated. Okay,
Yes, sir.
separated means like positive charges are separated from negative charges because of the resonant wavelength, because it is applying some energy, some force. It
Yes,
is
sir.
applying some force, electromagnetic radiation energy. So it's an energy. And because of this separation, there is this Coulombic interaction between the positive and negative charge. And because of this Coulombic interaction, there is an oscillation of the electrons. So why electrons oscillate? Because their electrons are lighter in mass. No, electrons are very light particles, very small mass, right?
Yes, sir.
and this results in kind of oscillation of the electron cloud
Mm.
about the GNP. GNP here means the gold nanoparticle. Okay, and such oscillation results in surface plasmon resonance. Okay, and here this is the light wave or the electric field generated due to the light wave. Okay, so we know that the electron is always no opposite to the electric field. Okay, so if the electric field is in this direction, the electron cloud is on the opposite direction, and here also the electron cloud is on the upper direction and the electric field is like this. And this results in also no, and also this phenomenon has some other implications like no electric field enhancement near the nanoparticle surface because of this such surface plasmon resonance, or because of this coulombic attraction, and then the restoring force which results in the oscillation of the electrons with respect to the about their mean position with respect to the gold nanoparticles. So because of all these things, there is an electric field enhancement near to the metal nanoparticle surface. Okay,
Yes, sir.
so that is a result of surface plasmon resonance. Okay, so let us now understand the definition. So I think in your thesis we have given more details about surface plasmon resonance. So what is written here? Oscillation of conduction band electrons due to light incident on metal nanoparticles giving rise to surface plasmon resonance. Okay. So oscillation of conduction band electrons, of course, the electrons have to be conduction band electrons due to light incident on a metal nanoparticle. So light has a frequency or wavelength, but here we are not using monochromatic light. We are using light, UV visible light. That means we are scanning over a wide range from 200 to 800 nanometers. Okay, and this results in and at a particular frequency of radiation, or which is also known as resonant. So resonance means when the frequency of light becomes equal to the frequency of oscillation. We know that every oscillation has a frequency associated with this. You have learned in wave and optics chapter, waves and optics. No, that was the name of your topic. You understood earlier.
Yes, sir.
So for a particle to oscillate or a body to oscillate, there must be a frequency. No? And resonant means when the frequency of the incident light is equal to the frequency of oscillation of those particles. Here the particles are nothing but the charge carriers, which are the electrons. No? Because we know metal nanoparticles have a lot of electrons in them. Okay. So this is more or less the definition of surface plasmon resonance. Okay. So have you understood more or less what is surface plasmon resonance?
Yes, sir.
Okay. Because when I mean like the resonant energy, because frequency is also related to energy. Okay, E equal to h nu. You would know this, no? Planck's equation. H is Planck's constant. Nu is the frequency of radiation. So when they get enough energy, so they oscillate about their mean position. But one more thing you should remember, that surface plasmon resonance is observed when, remember this, when metal nanoparticle size is smaller than the wavelength of radiation. Okay, so metal nanoparticle has to be much smaller than the wavelength of radiation, and in that case only we observe surface plasmon resonance. Okay. So now there is some a few information given here about surface plasmon resonance. So what happens with surface plasmon resonance? I have already mentioned the electric field near the metal nanoparticle surface is greatly enhanced. Okay, this is one reason. Greatly enhanced because electrons move from the positively charged particles, and then no, there is a so when there is a separation of charge carriers, then what happens? An electric field is generated, no?
Yes, sir.
And generation of electric field leads to the enhancement of electric field is enhanced near the metal nanoparticle surface. Okay, and one more thing, why surface? What surface Plasmon resonance? Because most of these electrons are on the surface of the metal, okay, or they are the conduction electrons. So that's why the word surface is used. And plasmon means the collective oscillation of electrons. Okay, now okay, I am again let me come back to this slide. So every word has a meaning here. Surface, maybe the external may ask, why do you call surface? What is a plasmon? What is a resonance? So surface, if you are asked what is a surface, that means
Yes.
most of these electrons are conduction electrons, then they are loosely bound, okay, loosely bound in a metal, or they reside on the surface of the metal, right? What is plasmon? Plasmon is nothing but the collection of these oscillating electrons, no, because there is not only one electron, there will be electron clouds, billions and billions of electrons, so their collective oscillation is known as plasmon. Okay, collective oscillation of electrons. And a resonance means because this oscillation, this collective oscillation of electrons is happening only at a particular frequency. Okay, only at a particular frequency of the light radiation, the electrons oscillate about their mean position, right? So that is why each word here, surface, plasmon, resonance, you are seeing here, each
Yes.
word has its own meaning. Okay. Okay, some information related to surface plasmon resonance. So electric field is greatly enhanced. Okay, at the resonant frequency of oscillation, the particle exhibits maximum optical absorption. Okay, I will come back to this one with a figure later. So surface plasmon resonance depends on a lot of things, like what is the particle size, what is its shape, what is the refractive index of the environment in which the metal nanoparticle is there, and also it varies from one metal nanoparticle to another metal nanoparticle. Okay, so different metals have different plasmon resonant frequencies owing to different electron concentrations. Okay, so surface plasmon resonant frequency expression is dependent on the numerical expression that is dependent on the electron concentration. Okay, so because of this, because different metals like gold is a metal which has different electron concentration than silver, and due to such a difference in electron concentration, they will also have different surface plasmon resonant frequencies. Okay, and colors observed in colloidal metal solutions is due to SPR. SPR means surface plasmon resonance. Okay, so in colloidal metal nanoparticles, we see why they are colored because of the surface plasmon resonance. So I have shown you one figure now where this figure here, why they are colored because of, now I'm coming back here, because of surface plasmon resonance.
Resonance.
And okay, so now the thing is one thing, if the nanoparticle or metal structure size is very big, we will not see surface plasmon resonance, or we will not see color. Why not? Because a big particle will trap different wavelengths in it. Okay, we know wavelengths correspond to color. Okay, and a big particle or a big structure will trap various different wavelengths in it. Therefore, we will not be able to see surface plasmon resonance in big metal particles. But when it is a nanoparticle which has a size much smaller than the wavelength of radiation, in that case what will happen, the nanoparticle, the small metal nanoparticle, it will trap only one particular color, and color corresponds to wavelength, and therefore for different sizes we observe different colors. Like here we can see some orange, we can see some reddish type of color, like this. Okay, so you now understand why they appear colored, because
Yes.
small nanoparticles trap only particular color, only one particular color. Okay, and one color corresponds to wavelength, and therefore they seem colorful, or they are colorful. They exhibit color. But when the nanoparticles are like big, very big, they like trap various different colors,
Yes, sir.
and therefore we cannot observe surface plasmon resonance. Okay, or surface plasmon resonance is generally not observed. So we have discussed this. So here, okay, this is the last slide we will discuss, and also last for you, because for you we will not go beyond surface plasmon resonance.
Yes, sir.
But for MSc students, they will also have to learn about
Raman scale power
surface
separate.
enhanced Raman scattering. Okay, so we have learned one particular line here. You see, at a resonant frequency of oscillation, the particle exhibits maximum optical absorption. Okay, so that is what we are going to see here. So here, these are 40 nanometer gold nanoparticles. Now I have taken this from a particular website. So here, what is going on? This maximum absorption. Okay, so like, can I see the sentence again? Resonant frequency of a particular maximum. So
Yeah.
resonant frequency of oscillation here, it is around I think 530, 520 to 530, this particular peak. Okay, so this is the maximum absorption. Here it is the maximum absorption, because here we have wavelength, here we have absorbance. So this is the maximum absorption for the 14 nanometer gold particles, okay, or 14 nanometer size gold nanoparticles. So we can see maximum absorption here, right? Hmm?
Yes, sir.
And that appears at around 520 or 30 here. So here, so this is the wavelength is plotted along the x-axis. So here it will be around 520, 30. Okay, so at around 520, so for this 40 nanometer gold particles, at around 520, 30 nanometers, we will see maximum absorption. Okay, so this is the curve of maximum absorption. And if you see such a strong curve in EV visible absorption spectrum measurements of gold nanoparticles, so this is nothing but surface plasmon resonance, right?
Yes, sir.
That is the surface plasmon resonance. So how do you observe surface plasmon resonance? So one of the ways to observe surface plasmon resonance is to measure absorbance spectrum like this, and you get strong curve like this. Okay, and this is the corresponding wavelength of absorption, 520 or 30, like that. Okay, so in this second figure, it is also same as here, this one. You can see peaks are of similar shape like this. But
Yes.
here we have different sized nanoparticles starting from 20, 30, 40, 50, 60, 100, 250, up to 400 nanometers. So let us understand a little bit here in next 5 minutes. So 20 nanometer, you see the blue one?
Yes.
From current slide. You see the blue one? This is the smallest nanoparticle, only 20 nanometer in size. But when you are increasing the nanoparticle to size to 30 nanometers, so it is the red one. Okay. Now for the 40 nanometer, it is the orange one. So again, there is this deep blue color. No, 50 is the green one. Sorry, there is one green. Sorry. So what is going on here? As you are increasing the nanoparticle size, the absorption peaks are moving towards longer wavelength. Okay, so smaller is the nanoparticle size, smaller will be the wavelength of absorption, but larger is the nanoparticle size, so longer will be the wavelength of absorption. Okay, so here 400 to 800, you see the wavelength is increasing from left to right. And you when you are increasing particle size, the wavelength of absorption, because we have learned from this figure, this is the wavelength of absorption. So this particular wavelength of absorption is also moving towards right, means moving towards the longer wavelength region. Okay, so when this happens, when does this absorption wavelength move to the longer wavelength region? When the particle size becomes larger. Okay, And also one another observation, as the particle size becomes larger, this absorption peak also becomes broader. Okay, not only so, when the gold nanoparticle size becomes larger, not only the absorption peak shifts to right, but the absorption peak also becomes broader. Broader means they become broader. Broad, broader, narrow, broad. No, you know that. Narrow means no, narrow means narrow. I don't know, and broad means broad. So you understand now this, no?
Yes,
So
sir.
what is the, and why, what is the reason for this? The reason for this is uh, nanoparticles become unstable, no, because this happens due to something called aggregation. What is aggregation in this case? Aggregation means two or more nanoparticles, they uh, coalesce with one another. Coalesce means they just join together with one another. Then they become larger in size. Okay, if they become larger in size, then what happens? The surface plasmon intensity kind of degrades, no? Or they begin to trap more wavelengths, not only one but more wavelengths of light, and that way they become broader in profile. Okay, no? They become broader in profile. And when you see one, two, three, four, these four peaks, so they are much broader, and not only one, but we can see two peaks. You see this brown color one. So there is one peak here, somewhere here, and this peak here. So this is around 150 nanometer in size. Because this is quite big in size, therefore we are observing such very broad type of profile, right? Why? Because the nanoparticles, gold nanoparticles, are no more stable, and stability means they are no more separate. Maybe 2, 3, 4, 5, or 10. I don't know how many nanoparticles they might have aggregated. I mean, they might have joined with one another, and that's why we can see such broad profile of UV visible absorption spectrum. And of course, when we measure, what is our aim to do? We aim to get this first two, three type of peaks, no? This blue one, red one, and the orange one. So up to 40 nanometers, if we can like limit the size of our nanoparticles, or like this, or here, the first three, then that is good. You can say that our nanoparticles are quite good in characteristics, are quite good in nature, okay, or usable. But of course, we don't want agglomeration to happen, or we don't want very big nanoparticles. Otherwise, their plasmon resonance is degraded like this, or they may have a very broad profile. Okay. So okay, here absorption spectra of 40 nanometer sigma rich gold nanoparticles of absorption spectra of gold nanoparticles of different sizes. Okay.
Optical
There,
density.
huh? Optical
Optical.
density is just a function to measure. I think it can be measured from this absorbance. Okay.
Okay,
I'm
sir.
not very sure about the formula, but instrument same measurement. This one and this one same measurement.
Okay,
You
sir.
see the peak profile is similar. No? So
Mm.
there is some way to convert this to absorbance to optical density. But right now, I mean, I don't exactly remember the formula, which I may check and give it to you. Okay.
Okay,
So
sir.
here are now some observations. We read these observations of this surface plasmon resonance. So first one is gold nanoparticles exhibit strong absorption peak due to surface plasmon resonance. Okay, like this one, no? This is actually very strong absorbance peak. Compared to semiconductor nanoparticles, this is very strong. Okay. Later, maybe you can check one of my YouTube videos uploaded recently. There I
Yes.
have shown absorption peak of zinc oxide, and compared to that, you will find that this particular absorption peak is much stronger. No? That is why we have written gold nanoparticles exhibit a strong absorption peak due to surface plasmon resonance. Okay. Then as the particle size increases, the absorption peak redshifts and peak broadens. So here, as the particle size increases, the absorption peak redshifts and peak broaden. Redshift means shifting from low wavelength to higher wavelength, lower wavelength to longer wavelength, okay? Or
Yes.
shorter to longer wavelength. Okay, first it is 20, then 30, then 40. So as you are increasing particle size, so we have discussed already, the peaks are moving from left to right. Left to right means they are absorption wavelengths are increasing from a lower value to higher value, and that is called redshift. Okay, this one also, this concept redshift or blue shift. Blue shift means like shifting of the absorption peak from longer wavelength to shorter wavelength. These things I have also discussed in the previous video. Okay, and peak broadens also. Okay, you have seen these peaks are quite broad, no, much broader than smaller nanoparticles size peaks, no? Smaller size nanoparticle peaks. Okay, the PR means plasmon resonance. PR peak continues to degrade in intensity and broaden further with particle size increase aggregation. So you so no there you see aggregation means like addition. No, when they combine, many particles combine, that is aggregation, and this plasmon resonance peak quite broadens. No, okay, quite broadens, or they degrade. No, they are no more significant like the plasmon resonance peak of smaller nanoparticles. Okay, so they can show quite broad profile. No? That is what we have written, degrade and broaden further. So aggregation causes conduction band electron to share among other neighbors. No, what happens during aggregation? Causes this conduction band electrons are generally within the same nanoparticle if the nanoparticle size is small. But if there is aggregation, what happens? This conduction band electrons can move from one nanoparticle to another nanoparticle, and thereby there is kind of destabilization. Aggregation leads to destabilization. Destabilization means opposite of stability or stabilization. So small nanoparticles, they are stable. Aggregation, they become destabilized. Okay, among other neighbors. Okay, as a result, SPR peak, surface plasmon resonance peak, becomes weak and redshifts to longer wavelength. Okay, and as a result of destabilization, the surface plasmon resonance peak shift to longer wavelength. No, this one what we have shown here already. Of course, this is not. These are not our results. These are taken from literatures or websites which have been cited already, because no, we could not do the measurements anyway. Becomes okay. As a result, SPR becomes weak and redshift. Okay, redshift already shown here. Also, broadening of the peak appearance of secondary peak is observed. Okay, you see, there is for these ones there is another peak of absorption. When the nanoparticle size is too big, so there is another absorption peak. No, this may be due to agglomeration or destabilization of the metal nanoparticles. Okay.